first, before I start, I wanted to thank the organizers for inviting me to give a talk here. And in particular, that it's about matrix factorizations, because that's like somehow how I learned representation theory, by first learning about matrix factorizations and then learning about Cohen-Macaulay modules and quivers. So probably the other way around from you. And so the goal of these lectures will be, well, to introduce you what is a matrix factorization. And so what they have to do, so I'll always abbreviate matrix factorizations with MF, and how they are related to those so-called maximal Cohen-Macaulay modules on hypersurfaces. And then also give you some examples and how matrix factorizations appear in representation theory. So this is my goal. And before I define what a matrix factorization is, just a very short history. I still hear myself, but I can ignore it. So the history is, so matrix factorizations were introduced by David Eisenbud at the beginning of the 1980s, so exactly in 1980. And so he he is a commutative algebraist, and he was interested in homological algebra on a complete intersection, so study of pre-resolutions essentially. And after this, there was also a lot of work following in commutative algebra in the 1980s, and then in connection to the Mackay correspondence, also a little bit in representation theory. And there was, a lot, I'll say probably more about this tomorrow. And then there was like a long time where matrix factorizations weren't used that much until homological mirror symmetry came, and Orlov, like I think officially 2009, but it was in the archive 2005, rediscovered matrix factorizations in the context of homological mirror symmetry. So this is homological mirror symmetry. And so I say hopefully also more about Orlov's theorem later, but basically, so David drew this diagram about the mirror symmetry of this A model and the B model, and the B model was the coherent sheaves on an algebraic variety, and that is where the matrix factorizations are, because if your algebraic variety X is a Calabi-Yau hypersurface, then Orlov's theorem actually says that this category is precisely the graded, stable graded category of matrix factorizations of the homogeneous polynomial f that defines X. And so this is how the matrix factorizations made a comeback into physics, and then more lately also in representation theory. Okay, so this was the part. And so now let's really start with 1. So I'm also trying to keep the numbering, but I think it should work for today's lecture. I'm not so sure about tomorrow. So first, what is a matrix factorization? And and I should fix my setting. So I will always talk about rings S and R, and so S and R will be commutative rings. And just to make sure, because Charlie is talking about non-Noetherian rings, I'll always assume that they are Noetherian. For the moment, they can be any Noetherian commutative ring, but later, very soon, S will always be something that is regular. complete local or graded polynomial. So you can always think about either complete local, so that is the power series ring over a field in n variables, or it is just the polynomial ring. And when I'm talking about the polynomial ring, then usually you work in the graded case. So why these two? Because in both of these you have the Schmidt theorem, so you can uniquely decompose modules. That's the important thing here. And R will be then most of the time something like a quotient of S, so S modulo some ideal. And so, well, if you look at S, a polynomial ring or power series ring, if you look at the homology of this is kind of a little bit boring because, for example, every module has a finite projective resolution. But then you might ask, well, if I go to a quotient, can I somehow see the homological structure of this quotient ring from S? And when you do this, you will see that, oh, well, if you look at if I look at all modules over R, this is something that is too hard to understand. So it's really big. And so you want to find some like nicer subcategory, and that's where the maximal Cohen-Macaulay modules come into the game. So once that is then this subcategory MCM of R, which are maximal Cohen-Macaulay modules. And so in the commutative context, let me just define what is a maximal Cohen-Macaulay module, because most of the time you just say, oh, these are maximal Cohen-Macaulay modules, and that's it. But the proper definition is, so if we have a local ring, so it's just if R has one maximal ideal, so local and always commutative, and then M is a finitely generated R module. Then one defines the depth of M over R to be the infimum of I greater or equal to 0, such that X of I of the field R mod M into M is not equal to 0. So you can also see that as a classical in commutative algebra, you define this with the length of the maximal M regular sequence. But so you can calculate this depth. And so this depth, you can show that this is always less or equal to the Krull dimension of R. And in the case when the depth of M is equal to the dimension, or to the depth of R, then dimension I'm making, so the dimension of R, then M is called maximal Cohen-Macaulay. Okay, and so, and R itself is called Cohen-Macaulay if it is maximal Cohen-Macaulay over itself. So this is what maximal Cohen-Macaulay is for us for the moment. And so the usual examples of Cohen-Macaulay rings, that's like, so everything that's regular is Cohen-Macaulay, then everything that's a complete intersection. But something that's not Cohen-Macaulay would be some ring that has, like, for example, embedded components. So this is Cohen-Macaulay, and then on this board, maybe I'll write the theorem that was already mentioned by Charlie, although in a slightly different formulation. So, I'll write it again. So it's Alexander Buchsbaum. there. So this was that's actually this Eisenbud paper. So this is from 1957. That's actually the first time when Cohen-Macaulay modules were called Cohen-Macaulay. And so this is the Eisenbud formula. So if we have a commutative local ring, and we take a finitely generated bar module, and that has finite projective dimension, then we have that the projective dimension of M over R plus the depth of M over R is equal to the depth of R itself. And so you see if R is regular, then you get the formula that Charlie had. So then I should erase that. And I'm erasing any questions. Sorry. Yes. Yeah. Okay. So now we're ready for the to answer that question. What is a matrix factorization? I'll define it. So let S be again a commutative ring, and we take any element F in S, and I'll assume that this F here, this is always a non-zero divisor. And then first one can define what's a linear factorization. Of F. So this is just a pair of S modules, S module homomorphisms. So I always write them A and B. So these are the matrices that this is that are involved, and there will be a matrix factorization of F. Such that we have a map from C0, C1, C0. So here is A and here is B. And these two maps have to satisfy the following. Yeah, maybe I'll still write it on this board. So it's complete here. Namely, we want that A times B is the identity of C0 times F, or F times the identity. And we can also multiply in the other direction. B times A is the identity of C1 times F. So they're like inverse to each other, but somehow this F is somehow not quite inverse. And then there's a linear factorization. So I should have said, so C0 and C1 are some S modules. And so if C0 and C1 are projective S modules, then this pair AB is a matrix factorization of F. And so we will only work with these matrix factorizations. So our modules F, C1 and C0 will always be projective. And then you might think like, oh, well, can they be somehow, can M and N have, A and B have different ranks, or like different dimensions. And so this is just as a remark, if, for example, C0 is just some S to the N, then it follows that C1 is also S to the N. So in fact, we always have maps from S to the N to S to the N. And so just another remark, if you come across this definition in the physics literature, usually this is denoted a little bit differently. So in physics, the category, well, I haven't talked about the category of matrix factorizations, but so they consider the category of, so this is a differential set to graded category. And so if you have a matrix factorization A and B of F, then they are usually encoded as in a 2n by 2n matrix Q that is of this anti-diagonal form 0a E0. And then you see, well, if we square this Q, then we get exactly those our two conditions, A, B, and BA. So Q squared is AB 0, 0, BA. And so this is nothing but F times the identity of S to the power 2n. And then this Q is then called the so-called twisted differential. So, so this is a different way to encode matrix factorization. So then I already mentioned they are categories. So if there should be a category, we need to say what morphisms between two matrix factorizations are. So here, so a morphism between two matrix factorizations AB and A prime B prime. Well, this is again a pair of maps. So it's a pair UV. So again, this should be S linear homomorphisms, such that we get the following nice diagram. So up here, so now I'm like always assuming that my projective modules are actually S to some power, which I can if I'm assuming that S is the polynomial ring or the power series ring. So here we have our original one, A and B, and down here we have A prime and B prime. And here are the morphisms. So U and V go here, and this diagram should just commute. Okay, so this is more or less what you would think a morphism should be. And so you can actually show, in fact, like it's enough to see that when this like right-hand square commutes, then automatically the left-hand square commutes. But in general, it's like surprisingly difficult to like find homomorphisms and to see whether two matrix factorizations are equivalent. So yeah, maybe I should say that at this moment. So two matrix factorizations are equivalent if U and V are invertible over S. So, and then you can form this category M F S of F. So this is the category of matrix factorizations of F over S. So, well, and so this is an additive category with, like, you take as addition, you just like take how do you say, block matrices. So now you know what a matrix factorization is, but well, this is just the definition. So let's give you some examples. Not necessarily, I think. No, thank you. This can be anything. Thanks. Yep. Okay, so then I'm not used to these many boards anymore. So I'm slightly lost. Okay. So examples. So there's one example which is sometimes called the mother of all matrix factorizations that everybody knows from linear algebra. Namely, if we take a matrix so an n by n matrix over our ring S, and we look at F as the determinant of A, and of course you have to assume that this F is a non-zero divisor, so S is the polynomial ring, then it's just, this condition just means F is non-zero. Then you can look at A comma A adjoint. So if you take the adjoint matrix, then this is a matrix factorization. Because, well, by definition, A times A adjoint is A adjoint times A is F times the identity on Sn. Then second example is you can always find trivial matrix factorizations, and there are two of them. Namely, you just take n equals to 1, and then what you can do is you can take your 1 and F, because 1 times F is F times 1 is just 1. So this is a matrix factorization, and then the other one, which is just exchanging the two F and 1. So these exist over, like, for any F. But then, yes, sorry. I should probably pull them this down. But a bit more exciting. Is then if we take a proper, like, if we take a polynomial, so also a cubic polynomial. So Charlie used the node. I'm taking the cusp here. So this is a polynomial in two variables. So you might ask, well, how many matrix factorizations can we find of this? And So, well, maybe surprisingly, there are not so many. There are exactly 3 up to equivalence, namely the 2 trivial ones, so F1 and 1F. And then we have a 2 by 2 matrix factorization that is of the form x y squared minus x. Okay, I have some sign problems here. What do I? If I'm up, no, I don't have sign problems. Seems okay. So you can only have 3 different ones, so finitely many. But in general, you will have infinitely many. Yeah, if you take a random polynomial, but then there was actually a question, if you take the generic determinant, so if you just look at F, the determinant of an n by n matrix with just the variables xi, j, so this is now living in the polynomial ring in n by n variables. And then I think it was asked by Bergman. The question was, is the only matrix factorizations of this generic determinant given by this xi and the adjoint? And surprisingly, this is not correct. So this matrix factorizations over the generic determinant. So if n is even, there are lots of them. And so if you want to see more, and I'm not talking too much about this example, but this was studied by Buchholz and Leuschke. And then from this example, actually, then Buchholz, Leuschke, and Vandenberg constructed non-commutative NCCRs for this generic determinant later on. Well, starting from these matrix factorizations and then using exterior powers. So these are some like very concrete examples, and yeah, then probably later I'll tell you a little bit more about about when we only have finitely many, and this will be in connection with the Mackay correspondence. Okay, so now we know what matrix factorizations are. We have some examples, and so the next step is, well, what do they have to do with maximal Cohen-Macaulay modules? So before we come to this, I need a little lemma. So somehow we have always these like F1 and 1F, and we want to get rid of them. So, and we can do that. So if we have S, as always, so complete local or regular complete local or graded polynomial ring, graded polynomial or complete local regular. Then if you have any matrix factorization of our polynomial f, we have A and B, a matrix factorization of f, then there exists some uniquely defined integers r and s greater or equal to 0, such that, well, we can bring A and B in the following form. So A and B are equivalent to something of the form. So we take here, yeah, I always wrote identity, so keep it that. So identity of S to the R, 0, 0, 0, 0. Then here we have F times the identity of S to, what did I say, S, yes, 0, 0. And here we have some A prime. And then to switch this, 0, 0, 0. Identity S, oops, S to the power S, and this is of course CBR. Hope it's still readable. And here we have B prime, such that, well, these two, so A prime and B prime, they are then of the size n minus R minus S, such that A prime and B prime do not contain unit entries. So we cannot somehow invert any element in A prime and B prime. So this is just to get rid of these of these parts here. And so now let's come to the maximal Cohen-Macaulay module. So this is now part 2. So maximal Cohen-Macaulay modules over R, which is now S modulo F. Okay, so the idea is that here, well, how they relate. So, well, what I want to show is that they are actually the same thing. So if I give you a maximal Cohen-Macaulay module over R, you can construct a matrix factorization from it, and the other way around. If you have a matrix factorization, you get a maximal Cohen-Macaulay module over R. And so so if we start with a matrix factorization, so this is some matrix factorization of F. Well, then, if you remember the conditions, so we have A times B is F times identity, and B times A is F times identity. So we're going to use them now, because from B times A, the identity, it follows that the identity times F. It follows that actually A has to be injective, because, well, F is a non-zero divisor, so you cannot divide through it. So if F is injective, if A is injective, then we get A injective, which follows from B times A is F times the identity of, well, Sn. So, then we have that we have this short exact sequence. So this is injective, and then, well, what we can do here is we can just take this to be the co-kernel of A, and this will be a short exact sequence. So this co-kernel of A, I'll call this LA. So this is a projective resolution of LA of length 1. So, so the projective dimension of LA over S is 1. And then, moreover, since we have the other condition, so A times B, so from A times B is F times the identity of Sn, it follows that actually F lies in the annihilator of LA, which tells us nothing else, that LA is actually also a module over the hypersurface ring. So this implies that LA lies in mod R. Okay, so now we nearly have this maximal Cohen-Macaulay, so we just have to like stick all the parts together and use Alexander-Buchsbaum. So since we assume that S is regular, we use Alexander-Buchsbaum. And well, what does this tell us? Projective dimension of S, L over S, plus the depth of L, I just write L instead of LA, is equal to the depth of S. So S is regular, so it's actually equal to the dimension of S. This is 1. And so we get that the depth of L is precisely dimension of S minus 1. And so okay, so it follows that yeah, so then you also need, you can like go through that this is originally over S. This is the same as the depth of L over R, and so you get in total, since the dimension of R is dimension of S minus 1, so you get that the depth of L is the dimension of S minus 1, which is the dimension of R. And so as we have seen at the very beginning, this just means that L is maximal Cohen-Macaulay over R. So first part is done. So a matrix factorization gives us a maximal Cohen-Macaulay module over R. So then the other direction, it's always L of A. I just suppressed the A because there is no other L. So the other direction, so if we start with L, a maximal Cohen-Macaulay module over R. So R is again S mod F, where F is a non-zero divisor. Then, well, we can again use Alexander-Buchsbaum over R. And this tells us if we, wait, maybe I shouldn't call that L, I call it M, just to avoid confusion. So Alexander-Buchsbaum over R over S gives us that the projective dimension of M considered as an S module is 1. And then if we have that any projective module is a free module, that means that we get a resolution of it. So we get a map from Sm to Sn such that the co-kernel of A is isomorphic to M. And so as an S module, I get the following resolution. So here, yeah, M has again to be equal to N, follows from the rank consideration. So this is equal, so you can figure out yourself. So Sn A M 0. And so we have now like kind of the first map in a matrix factorization. So how do we get the B? Okay, this is now I'm gonna have maybe like 2 more minutes, 4 more minutes. Okay. Oh gosh. Okay. So so we have this map, and so now okay, I'll just draw the diagram, and then so you can draw this nice diagram here. So F times the identity here also F times the identity. So we have here the same diagram. Here we have the map 0. And so we see here, this is what we have. And then actually, so here we have A. You can show that there exists this map B, which is actually a homotopy between like this complex here, when you take the 0 here, and the lower complex. And so you can reconstruct the matrix factorization from it. So this is a homework how that this B is actually well defined. So it follows, you get a matrix factorization A B from M in MCMR. And so M is now the co-kernel of A. Okay, so these are the correspondence. And so I just want to I wanted to say a little bit more. I wanted to actually come to Eisenbud's theorem, but probably I don't have time for that. But at least I can say something about now resolutions. So resolutions in the sense of projective resolutions, not resolution of singularities, over this R, which is a hypersurface ring. So R is S mod F. So over S, we have somehow, this A and B are injective. But actually, if we go down to R, so if we just tensor this with R, then, well, what will we get? So if we start with our matrix factorization, AB, and then we take we tensor this, so just tensor this here with R. So what happens is the following. So, well, to M nothing happens, but in the back we get that, whoops, I called this C0 before, I just call it Sn. So here, Sn tensor R, Sn tensor R. So here we have A. Then this is going down to, and so on. So what we get is a 2-periodic resolution of M. And so the conclusion is whenever you take a maximal Cohen-Macaulay module over this hypersurface ring R, it has a 2-periodic resolution. And then maybe I can say Eisenbud's theorem, which says that now if you take any module over a hypersurface ring, well, if you look at the resolution, then what happens is, maybe I'll just state the theorem. So we have S again, regular, local, complete, and so on. And so the minimal resolution of any finally generated R module becomes periodic of period 2, so 2-periodic, after at most dimension of S steps. And well, the periodic part, so basically the idea is you take the module M and then you take the projective resolution, and in each step the kernel of the maps, the depth is going up. At some point, you reach Cohen-Macaulay. And so after dimension of S times Sept, your kernels are all Cohen-Macaulay. And so you have reached this maximal Cohen-Macaulay module. And yeah, and this periodic part is given by the matrix factorization. Okay, so that's all.
From here, locals.
Thanks. My question is, are there many cases when all the matrix factorizations are known?
That's for tomorrow. So, well, it's like there are a lot of cases when there are only finitely many are known. And yeah, then there are 2 examples of countably many, and the rest is just wild. And so usually it's like you cannot then classify all maximal Cohen-Macaulay modules, but sometimes if you go to like even a smaller subcategory, then you can like find some nice representation theory there.
Great, thank you. We'll look forward to that tomorrow.
Okay, so thank you, Eleonore, for a great talk. Are there any questions from the Zoom audience?
So I have a little question. So we only consider the matrix factorization over just a local complete ring or just polynomial ring, right, in our lectures?
That's mainly because of the Kroll-Schmidt theorem, which didn't, I mean, I kind of used it here that I can always uniquely decompose the matrix factorizations into like this A prime and B prime. So but, yeah, it's so you needed to say that direct sum decompositions are unique essentially.
Yeah.
But
so,
of course you could define matrix factorizations over any ring if you want to.
Okay, I see. But in the the context of the homological mirror symmetry, is so the matrix factorization only happens over like the complete local ring, or
I'm not sure if I understand the question.
Because you said in the homological mirror symmetry there is equivalence of categories, right? Like a matrix factorization of something in the derived category of the coherent sheaves.
Yes.
And in that context, so the matrix factorizations only happen like over just the complete polynomial rings.
Yes.
So, okay.
At least where you can at least say something.
Okay, I see. Thank you. Thank you very much.
I hope. I'm not sure if I understood the question.
Okay, then let us thank the speaker again. All right, and then we meet for the last talk in 5 minutes.